Computer audio. Oh my goodness. Sorry, we're having some weird technology issues here. Zoom crashed on me and I just pulled it back up. Stop live stream. It looks like we're recording though, so we should be all set. Sorry, that was really odd. Okay, I think it's working now, but just to double check, how's things working out in Zoom, folks? I think I had a weird crash on the client. Is it everything coming through, audio, visual, okay? I'm kind of dicey at the moment.
Yeah, I can see everything just fine and hear you.
Awesome. For that. Thanks, Braxton. It's always a little bit dicey when the whole thing crashes, and I'm not too sure if anyone's even able to see so far. So appreciate that. Well, let's get back to right over here where we're left off. We were in section 1.4 and we finished that one off. So the corresponding assignment 4 is posted right below. Also, assignment number 3 is coming due today. And I did mention, or I might have forgot to mention, but it's worth repeating. These due dates are, or these times on the due dates, they're really, well, I had a selected time and I didn't want to put 11:59 p.m. since it feels like I'm encouraging people to work really, really late. I just had to put something there. So I put the time class starts. But as far as the due dates really go, as long as you get your file into me or a hard copy into me on the day of January 25th, that's the real due date. So it just has to be sent in on that time. So don't worry if you have to send in email things a little bit later, stuff like that. I would understand. And especially if you ask a question in class, I'd understand you might rework a problem. You might need additional time. It's better to do that after class so you're not, say, missing the discussion on a current problem while you're fixing a homework problem. So if you have questions on a homework assignment, folks are always welcome to ask. And if you have to rework your assignment, you can just hand it in sometime in the evening. Also, another reminder, we're working homework assignments out of the 6th edition. Some folks might have saved a lot of money buying older editions, which still work great. But to get your problems from the 6th edition, click on this right here, assignment 3, and it'll pop out the exact exercises in the edition that we're working. It doesn't seem like that should be such a big deal, but if you even go back to the 5th edition, these could be totally different problems. Then, I mean, that doesn't seem bad either. One problem might be good as the next, except sometimes these problems change quite a lot. And these are picked very, very specifically to support us on the exam. So doing the wrong number 10, that could come back to us on an actual exam if we do a problem like that one, similar in spirit on the actual exam. So be sure you're solving problems from this PDF if you have an older edition. Aside from that, I think that's the only announcements I had for us today, folks. We're going to be in section 1.5. The assignment number 5 is now posted. So I'll turn it over to the class. Any questions or comments at the moment? Okay, well, let's get started in section 1.5. Now, before we get too far in there, let's take a look at 1.3 just for a moment. Because it's always good to kind of orient ourselves on where are we going in linear algebra, because at the moment, it feels like it's been definition after definition, theorem after theorem, but there's an organization to all of this. And here's where we're at so far. We're dealing with spanning in the prior sections. Now we're going to look at how to get to linear independence through section 1.5. And here's how it's structured so far. To get to linear independence, we need to solve something like this. Ax equals 0. And we have to decide, is there trivial or non-trivial solutions? The answer to that question, as weird as it seems, is what's going to address are the vectors in the columns of that matrix A linearly independent or not? It's going to come down to the matrix equation, which we just so happen to have studied last class. So we're going to now address trivial versus non-trivial solutions. Then when we come back next week, we'll be looking at linear independence. Well, any questions, folks, at the moment? Okay, let's jump back in then. Here's how section 1.5 starts. So we're looking at a matrix equation. We did that good work in section 1.4. And we hinted a little bit that some systems of equations are extra special. These are the homogeneous ones. It says a system of linear equations is homogeneous if you can write that system in this format. So essentially what makes it homogeneous is the zero vectors on the right-hand side. That means as a system of equations, by equation, all of your right-hand sides have to be zero. And just to be specific, we're talking about the zero vector with m entries coming from Rm. So that's our setup so far. That's really our core definition of this section. And for just a quick example, it says, let A be a 5x3 matrix. And we want to find one solution to that equation, which doesn't even seem fair in a certain sense. We didn't say what the matrix was, but we can still find the solution because we're taking some matrix A times X. And if you're insisting on getting the zero vector as your right-hand side, there's always one solution to this guaranteed. Anyone happen to know what X should be? It ought to be zero, just like ordinary algebra. If this was an equation like, say, 5x equals 0, x has to be 0. But that's the scalar equation we're looking at here in the pencil tool. Here, we're looking at a whole-on matrix equation. So we need to be pretty specific. It's definitely the zero vector. So I'll write out this way. We should say which zero vector. There's loads of them, for example. You could have the zero vector in R2, the zero vector in R3, and so on. One hint on that is we can take a look at the size of the matrix. It's 5x3. Now, it's being multiplied by a vector x. That implies immediately the size of that vector. There's only one way to get the multiplication to go through. X has to be of size 3x1, no matter what. So that those match up. Then when we go over here, we're going to have something of size 5x1. This is a little bit jarring, but it's kind of common for linear algebra. The number 0 is overloaded in the sense it could be a scalar, like over here, could be a vector, but it could be a vector of different sizes. This is a vector in R5, so it has 5 components, all 0. However, this one is a vector in R3, so it would look like this. 0, 0, 0 in R3. So we did it, folks. We found the solution. We don't even need to know what the matrix represents right here. Same over here on this equation. We could have just put an arbitrary constant like A, and still X has to be 0. In fact, let's do that. Just for a little bit of parallelism with an example, if it was an arbitrary scalar A multiplying X, X is still 0, just like over here with the arbitrary matrix. Now this X right here that we just found is also extra special. We found it with really no work, right? We just had to observe if the right-hand side is 0, a 0 product property ought to still work in some sense. And here it is, let X be 0, and you've got a solution. So this is called the trivial solution. It's kind of a weird name. It's an important solution, but it's trivial in the sense that it's always available. You didn't have to work hard to find it. It was trivial effort to get that 0 vector right here for a solution. So now we're suddenly extremely interested in this equation and whether it has trivial solutions, or excuse me, whether it has non-trivial solutions. This will always have a trivial solution. This is an important enough comment. Let's put it in. A homogeneous system of equations always has the trivial solution. One thing that's tough about this is it's easy to just say trivial solution over and over again, but keep in mind when you say trivial solution, what you're looking at is this. So it's good to put in here X equals the 0 vector just as a reminder. Once we start saying trivial solution, we're meaning that one. So now that we've got trivial solutions, here's the next concepts. We're going to bring in the existence and uniqueness theorem as well, and this might as well go on the next page. It's not quite going to fit. Okay, here we go. So it's a big wall of text right here. Let's work through this slowly. We define the trivial solution here, and it's the 0 vector that solves this system of equations. So what we really want to find, though, is non-trivial solutions. This is going to tell us a lot about the vectors inside the matrix A. So if there's a non-trivial solution, we mean a non-zero vector x still satisfying this equation. We already know the trivial solution will solve that. But now it's going to get boiled down to information about this theorem. Now we have to remember there is a trichotomy here, right? As soon as you look at a system of equations, ax equals anything, three things can happen. Either there is no solution. Well, we have to eliminate that one. A homogeneous system of equations always has a solution. So that possibility is out. The second thing that could happen is there could be a unique solution. If there is a unique solution, it would be exclusively the trivial solution, x equals 0. And the third possibility is going to be, well, there cannot be two solutions. You can't have the trivial solution and exactly one non-trivial solution. So there'll be infinitely many. Solutions. But if there's infinitely many solutions, you have certainly found infinitely many non-trivial solutions at the same time. So we need a way to detect when those are going to occur. And it turns out to be really fast. We go to the existence uniqueness theorem. That highlighting looks crazy. Let me take it off. And if the system's consistent, we know we're not going to deal with this ever. In fact, it's impossible. You can't get a pivot there because the right-hand side consists exclusively of zeros, nothing else for the homogeneous system. So it's going to boil down to this. If there is a free variable, then sure, there's infinitely many solutions. And that means there's going to be non-trivial solutions. So that's what it's all going to boil down to. If there is no free variable, then the system will only have just the trivial solution. So we'll say here, in this case, let's say it this way. Here, the system has only the trivial solution. So this becomes a bit of a mantra, and we're going to see it really reinforced in the section on linear independence. We'll look at and say, if there are no free variables, only the trivial solution. However, if there is at least one free variable, we will pick up non-trivial solutions. So that's our big theorem right down below to pretty much paraphrase everything we're looking up here through the definitions, existence uniqueness theorem. You can really just summarize it right here. This becomes a very powerful theorem in this section. So powerful, we'll give it a try and observe just how fast this works with that augmented matrix there. Well, any questions, folks, so far with the definitions? Okay, so we've got, looks like a 3x4 system. It says determine if the system whose, we have to worry about this word right here, whose augmented matrix is given here, has a non-trivial solution. One thing I would do to kind of just organize my thoughts on this is, first, definitely augment that thing with a little bit of a dash as just as a reminder. It's not required, but sometimes that helps out tremendous. And because we're talking about a non-trivial solution, one question you might have is, solution to what? All we're looking at is an augmented matrix. It really helps the mind out to actually write down the equation to get started. Let's write out ax equals the zero vector. So that's the system we're looking to solve. When we wrote the zero vector, we're looking at this portion right here of the system. This portion is going to be A. And we think of this column belonging to x1, this column to x2, this column to x3. And that's what's going on with x. X itself is the vector x1, x2, x3. So this is the review of what we were doing with the matrix equations. If we're going to solve this equation, and that's your matrix A, well, it pretty much just boils down to that right there. That's the augmented matrix we're going to work on. It feels weird we kind of went backwards, but if a problem just gives you an augmented matrix, it's good to think in these terms. It came from this matrix equation right here. But here's how the process starts. We take A, augment it with a zero vector. That's if we were looking right over here. But then we're right back to where we started, right in that spot. So let's go 2, -2, 4. I'm really just copying that whole matrix. -5, -7, 2, 8, 1, 7. Then augment it with the zero vector, so 0, 0, 0. Now we just begin row reduce, and honestly, this is a question we could have done week 1 in the class, but we just didn't order our definitions to talk about trivial solutions in week 1. The author just left it for this week here. So in solving this thing, well, it looks kind of interesting. One thing we have to decide is, what are we going for? Do we need reduced row echelon form or just echelon form? Can anyone tell which method we need? Well, it turns out for this situation, we just need ordinary echelon form. So if it wants to determine if it has a non-trivial solution, what we're going to look at is if there's a free variable or not. And that means all we need is an echelon form. We don't need to go to the full reduced. So we'll say here, this is always a good reminder for these questions, because that's one thing that's tough about linear algebra. How far do we reduce? I'll always try to put indications here, usually in an orange pen. So let's put it here. Whenever you're being asked if a system has a non-trivial solution, all you need is an echelon form for this question. However, we will see questions in these notes where we're going even further, reduced row echelon form. So watch out on these notes and on the homework assignment as well. We'll be doing similar things on the assignment. Well, that's good news because we're dealing with echelon form. Back over here on the pivot, we don't need to worry about making that a 1. It's okay as a 2 for an echelon form. So all we are going to do is take row 1, add it to row 2 to start. So here's our row equivalence operator. Go 2, -5, 8, 0, row-wise. Take row 1, add it to row 2 to get 0. Then that's going to be -12, 9, 0. The next operation, we're trying to eliminate 4. So multiply row 1 by -2, add below. We'll get 0. -2 by -5 is 10 plus 2 for 12. This is -16 plus 7 for a -9. Let me know if my arithmetic goes sideways. It's really easy to do when you're dealing with a night class. And then zeros. One thing that's kind of special about this is for dealing with a homogeneous system, you have a 0 vector here, then you augment with a 0 vector here, and you'll observe there is no possible way to change these. It's always going to be 0 no matter what we do here. So why do we copy them in? Turns out that matters a lot, especially for something we're going to do down below called parametric vector form. Not having those zeros there can become just a sudden confusion that we don't necessarily want in linear algebra. So as a best practice, even though it's not strictly required, I would encourage you to put in those zeros, even though nothing's happening with them. It helps us when we're going for the next problems we're going after. So let's continue to row reduce. We have a pivot here. Our next pivot is in this location, so we need to eliminate 12 below. It's not so bad. We'll add row 2 to row 3, so it's going to go row equivalent 2. First, I'll copy in row 1, 2, -5, 8, 0. Copy row 2, so 0, -12, 9, 0. Now this is the fun step. Add row 2 to row 3, and we get nothing but zeros. So here's where I'll put in the augmented. We really need to see that in order to clearly see if there's a free variable. Column 1 is for x1. Let's do some highlighting here just to make this pop out a little bit more. So column 1 is for x1. Let's put that here. Column 2 is for x2, and column 3 refers to x3. And we need to decide, are there free variables in this setup? Absolutely, we have x3. x3 did not correspond to a pivot whatsoever. x1 did, and x2 did. So x1, x2 are called the basic variables. That is an honest definition, but you might notice that it's not used a lot. The reason is we're more interested in the free variable. So x3 is free, implies, well, let's take a look. There's going to be infinitely many solutions once we have a free variable, if you're thinking of the existence uniqueness theorem. And in that case, there's automatically non-trivial solutions. If we're only looking at this theorem, that's just fine. You'll have non-trivial if and only if we have at least one free variable. So the moment you find free variable, it implies there are non-trivial solutions. Then a problem finally ends right at that step. Any questions about the approach on getting through this so far, folks? Okay, so a lot of row reduction, linear algebra so far. But one thing I want to leave us with on this problem is, this is a larger question like what we've been hinted at. If we were in section 1.7, we would make another determination. And what we're going to eventually conflate this with, it helps to see it now, even though it's a preview. If you said that there are non-trivial solutions, it means, I'll put this in parentheses to indicate you don't have to say this in your work, but this means the columns of A are linearly dependent, which has its own interesting set of consequences in linear algebra that we'll explore in the upcoming sections. So that's really the major reason we're talking about non-trivial solutions versus only having the trivial solution. It says something about the columns of A that we're going after in the next sections. Well, we did it, folks. That's our preview or big technique so far. If we go on down to the next problems, really we're just looking at that a little bit more on our example 3 here. We have on a system of equations. It's a little interesting because there is a parameter right there, h. We've dealt with that before. So somehow the question is going to settle around h some way, somehow. But sometimes the harder questions are these ones right here. These could be honest exam questions, really short, fast concept questions that circulate around the definitions or some easy theorems. And this is a question that I have asked quite a lot on the real exam. We have a system and we're wondering, can the system be inconsistent? Is there any possible way? Anyone see if that's a possibility for this system? It's tricky when you look at it in this format, right? Because we're just not used to this notation, really. When we see this kind of notation, the original equations, very first thing we do is we throw it into an augmented matrix or we write out a matrix equation. If we wrote out a matrix equation, it would be AX equals the 0 vector. A would be a matrix of coefficients formed from all these coefficients on the left-hand side. But now you see that, this thing has a name. It just didn't seem so apparent when we look at the system of equations. But either way you look at it, we have a homogeneous, let's say it this way, this is a homogeneous system. And one important feature of a homogeneous system is it will always have a trivial solution, guaranteed. And we can kind of visualize it. Let x1 be 0. Over here, set x2 to 0. On the next one, set x3 to 0. And that's automatically a solution in row 1. It will work in row 2, and it will work in row 3. So if we're not thinking of a vector, we could just indicate the results for all the values here. That might be how you're thinking about it if you're just working with the equations. And this is a solution. So it's impossible for the system to be inconsistent. Or another way to think about the question at the moment is, no matter what number you pick for h, you'll always have a consistent system because we found the solution right here. It just so happens to be the trivial solution. Let's write that in just as an extra comment. That is the trivial solution. Well, any questions, folks, so far with the concept question here? Okay, let's go off next to we want to know for what values of H will the system actually have non-trivial solutions. So that's going to be our next step. But really, it's kind of a just redo of this. If you're looking for non-trivial solutions, we'll reduce to echelon form, see what the pivots look like. And so we're trying to arrange our pivots so that we will have a non-trivial solution. We're arranging for a free variable with the right choice of H, in other words. So that's going to be our next steps. First thing we do is take all that and immediately augment it. So it'll be for column 1, 1, 2, negative 1. In column 2, it's 2, 5, 1. Then 1, 3. Now H, that's the weird thing in there. Finally, we're augmenting with the right-hand side, 0, 0, 0. Might as well tie everything in there in yellow. That's what we mean by a homogeneous system. And then just begin row reduction. Again, we only want an echelon form. It always pays to write that out just as a reminder. And here's how it's going to begin. We'll copy in our row 1. It's 1, 2, 1, 0. Then multiply by -2, add to the row below, and we'll get 0, 1, 1, 0. Let me double check. That's -2 plus 2, 0, -4 plus 5 for a 1, -2 plus 3 for a 1. Looks like that works. Now take row 1, add it to row 3, and we'll get 0, 3, H plus 1, and finally 0. These are always a little bit clunky to write in just right because it's one entire algebraic thing that goes in one spot. If it was really more values, we'd put more spacing to show it's H and then a 1, for example. But let's keep on row reducing at this stage. We have a pivot here, pivot here. So this is the last operation. We just need to eliminate 3 down below. So for row 1 and row 2, first start 1, 2, 1, 0. 0, 1, 1, 0. And here's our last step. 0 will go through here, multiply by -3, add below to get 0. This one will turn into a -3, plus the 1 is a H minus 2 altogether. And then 0 on the right-hand side. So we've got it, folks. This is our echelon form. And as it stands, we have a pivot here, but this one's questionable. It might or might not be a pivot. It's most often a pivot, but what are we looking for? We have to be careful with instructions. It's conceivable the instructions could say only the trivial solution. If it said that in a homework problem, you would have to say H not equal to 2 to have only the trivial solution. That way, every column is a pivot column. There is no free variable, and that means a unique solution. When you say unique solution now, you're referring to this one, the trivial one. So we want non-trivial solutions. That means there is a free variable. Forget we're color coding that in blue, since that's the important concept to tie together. There's a free variable, and so there are non-trivial solutions when H equals, and we recall what it has to be, or not quite 0, or yeah, you'd have to have a 0 right there is what you're meaning. Exactly. So H would have to be a 2. So we did it, folks. That's another way to look at this same problem, but now, well, we've got the same kind of result. If H is 2, something happens to these columns. They become linearly dependent in this system. Well, any other questions or comments, folks, on looking at non-trivial solutions? Okay, let's keep on practicing these kinds of things. Now that we have an idea of finding non-trivial or detecting non-trivial solutions, one thing we haven't done is actually express what the non-trivial solutions will really be. Though our premier technique for expressing them is going to be this right here, the parametric vector form. But looks like before we get there, I forget, we have one additional theorem we want to take a look at. This is kind of a strange problem, but I put this problem here in the notes because sometimes the author says in his instructions, try to use as few row operations as possible. He's not meaning try to skip a lot of steps or find the fastest approach. What the author is really trying to say when he says use as few row operations as possible is there might be a theorem out there that tells you the conclusion to your system without row reduction. If you can find that theorem, then skip the row reduction and just use it. I forgot why I had white space here. Let's put back the white space and let's take a look at how this theorem goes. So we have a homogeneous system, A times X is 0. A is going to be of size m by n, so m rows and columns. And it says here the number of columns n is bigger than the number of rows m. Let's sketch something that looks like that. So we want a matrix to have m rows. So we'll go 1, 2, 3. Well, we don't know how many rows there, but let's just say m. I'll kind of visualize it this way. We have n columns, but there's more columns than rows. So let's go 1, 2, 3, 4, 5. So now it is unbalanced. We have more columns. So here's our n columns. Let's just fill out the rest of where those entries would be. Okay, so there's our generic matrix. Now they tell us if you have more columns than you actually have rows in your system, there will absolutely be non-trivial solutions. And here's the justification for that. Let's imagine we have the best case possible for pivots. Pivots would go about like this, down a main diagonal, but we're eventually going to run out of places to set a pivot when we hit our very last row. If there is an additional column, then this variable or this column corresponds to a free variable. But now we have to say, if there is a free variable, you automatically have non-trivial solutions. So our conclusion is, therefore, AX equals 0. In this arrangement, more columns than actual rows has non-trivial solutions. And in section 1.7, almost the same exact theorem is going to say, if you have more columns than rows, your columns are linearly dependent because of the non-trivial solutions. So those are two concepts that begin to go together quite a lot. So on this example number 4 right here, there might be a homework problem just like this one. It says determine a system whose augmented matrix, we have to always watch out for that, is this one, has a non-trivial solution. Because it's augmented, I'd probably just put this in on my work if I was doing it on paper. But this is a fast problem. You might say there are 2 rows and 3 columns. The next thought you might put in is more columns than rows. Again, that's what we're saying over here, n being the columns, n being the number of rows. More columns than rows implies AX equals the 0 vector has non-trivial solutions. Then that whole problem is over. We didn't have to even touch this with row reduction. In fact, the entries in this matrix are now irrelevant because we have too many columns. It doesn't even matter what you put in that matrix. This is the foregone conclusion. Kind of a fun problem. And again, this is why linear algebra is kind of weird. Notice we answered this question using words. There's a couple of numbers there, but the numbers are getting sparse. So it's kind of strange. That's not this whole course, but it's a feature of what sometimes we encounter in this course. Well, any questions at all, folks, on the conclusions here? Okay, now that we have that, let's take a look at it a little bit more. One thing I put down in my conclusion was the AX equals 0. It's not required in your work, but it's a good thing to think about if you get a problem that just throws an augmented matrix at you. It's good to think of the matrix A as that portion. We have a vector X there. We have the 0 vector, that's what makes it homogeneous. And when it said we have non-trivial solutions, let's just put in parentheses what we mean. This means there are solutions X in R3. R3 is because A is of size 2 by 3. So X has to be of size 3 by 1. So X comes from R3. Non-trivial solutions means we have vectors X in R3 such that X equals, or rather is not equal to the 0 vector. So it might be like 1, 1, 1. It might be a potential solution. We're not sure. We'd have to solve it to actually find them. But again, that's one thing we really haven't done very much of this course. What are the non-trivial solutions? That's kind of might be something that's gnawing at you at the moment. But don't worry, we're about to find them and show the process. So the process is parametric vector form. That's a heck of a word, and it's important enough that we mention it right here in the assignment. Be sure your solution sets to those exercises specifically, those are the ones where we're finding the non-trivial solutions. Be sure to express your answers in parametric vector form. It's a notation thing, but it's even more than that. The technique of getting things into parametric vector form is going to be used a lot. We'll be using it to find null spaces, eigenvalues, all sorts of things in chapters 4 and chapters 5. And so this is one of those techniques where it's a make or break kind of thing. It's very tough to pass this course with this being foggy in our minds. So let's put this in assignment just as a good reminder, or not an assignment, the actual notes. And let's give this a try. So remarks here are just saying this is gargantuan in importance, understanding and executing a parametric vector form for your solutions. And when we do this, here's the reminder of the echelon form we need. We'll be using reduced echelon form. So now we need pivots above and below, or excuse me, zeros above and below our pivots, and our pivot points have to be exactly a 1. So it says here, write the solution set of the system in parametric vector form. We're almost exclusively we are exclusively going to be doing this technique when there's a 0 vector on the right-hand side. In linear algebra, a lot of definitions come from this right here. And so that's where the form shines. First thing we do, though, is what you're probably expecting. This is something we could have done in the first week. We take the whole thing and we throw it in an augmented matrix, start row reducing. So let's put in for column 1, 1, 2, negative 1. For column 2, it's 2, 1, 1. Column 3 is negative 3, negative 3, 0. And here's the 0 vector augmented in. This is a very touchy procedure, and I'm going to show a lot of steps. I would encourage you to possibly reproduce all of them when you do the homework assignment, but only on this assignment 5. Once you start to see the shortcuts, you're welcome to take a lot of them as you see the process. But really learning the process, getting it into your mind is just a matter of really taking these steps. So I'll put here, just as a reminder, x1, x2, x3, all those values there. At the moment, we're just going to do ordinary row reduction, so eliminate values below that first pivot. So row 1 first is 1, 2, negative 3, 0. Take negative 2 times row 1, add to row 2 to get 0. Here, this will be negative 4, so a negative 3. Positive 6 minus 3, so positive 3, and 0. Next, we're adding row 1 to row 3 to get 0. 3, negative 3, 0. You'll notice there's usually not a lot of fighting in these. The numbers are rigged pretty well. Same goes for the homework assignments. They should be pretty fast row reductions. You might have a couple additional steps, but nothing too major. So we have a pivot here. And on this one, I'm going to do something that you're allowed to do on your homework. Let's take 2 steps at once for row reduction. This is a good opportunity to do that. Here's how we can start. I want to copy in row 1, 1, 2, negative 3, 0. My next operation is, I know that has to be a 1, but the numbers below it are arranged so nicely. Let's take row 2 as it stands and add to row 3. If you did that, you would get 0, 0, another 0 here, that's even nicer, and 0. Now, next thing I want to do is, because we're going for reduced echelon form, divide by negative 3 at this stage. You would get 0, 1, -1, 0. But that is two row operations at once. Does that make sense to folks on what we did there? Awesome. If those kinds of things are making sense, you must have been doing lots of row reduction, so good on you. I appreciate your work ethic. And you're absolutely welcome to do that in your work as well, even on exams. If you just see a couple things that you can just cram into one step, I'd say take that step. So let's take a look. It's still not in reduced echelon form, and we haven't done these a lot, so no worries if it's kind of a foggy concept. We're okay here. There's only zeros below the pivots. On the next pivot position, we need a 0 below, but we also need a 0 above. So our last thing is to eliminate that 2 right there. So we'll say we have row equivalents. I'm going to copy in row 2 and 3 to start. So 0, 1, -1, 0, and 0, 0, 0, and 0. Now finally, we'll take -2 times row 2, add it to row 1 to get 1, 0 here. It's -2, so that's a +2 minus 3 for a +1. Add that as 0. Here's where the pivots land in this column, and that's it. That means we have a free variable, so infinitely many solutions. In fact, loads of non-trivial solutions. Here's where we'll bring back x1, x2, x3, because now we're just reading out the rows. So row 1 is going to read x1 plus x3 equals 0. And here's where you have an opportunity to save a step. You could just solve for x1 immediately instead of writing this. But for a paper trail in the notes, I'll take this step as we practice this brand new technique. Next on row 2, go x2 minus x3 equals 0. And for row 3, it's true that it's 0 equals 0 as an equation, but what is more helpful for us is just to say x3, something about it. We have a statement about x1 here, x2 here, and x3 here, and that should happen each time you're doing parametric vector form. If those are the values, they should be read off in this kind of way. But what would you all say for x3? What word would you put next to it? Exactly, this is any real number. You could paraphrase by saying x3 is free, or you could write x3 equals x3. So anything like that would fully qualify what's happening with x3. Let's say it is free here, which means it's any real number in R. And now we take this next step. We're going to solve for the basic variables in terms of the free variable. Let's put some highlighting on this to show. The free variable is x3. There is no pivot associated with it. It appears here, here, and here. These are the basic variables that were associated with the pivot, and we need to solve them. So it'll go x1 equals -x3. Finally, x2 equals just x3. And this next statement is silly looking, but it's actually helpful. If x3 is free, it can be anything. So I'm going to write down an equation that expresses no constraint on x3 whatsoever. It looks really funny. x3 equals x3. No conditions. Pick at anything you want and you're all set. But once you pick an x3, you've also determined x2 and you've also determined x1. So x3 is controlling every single solution to the system. If you pick 0 here, you have found the trivial solution. Everything is 0. Put in a 1, that's a non-trivial solution, and there's infinitely many. Any real number goes for x3. But we're still not in parametric vector form. We need an additional step. Well, an additional set of steps. We have x1, x2, x3 here, but we're going to write out our answer as x itself. We want a vector x. If we specify a vector x, we need to read out x1 through x3. But now we have values for x1, x2, x3. We're just going to throw this stuff in. This will be equal to -x3, x3, x3. And this is looking pretty good because we have specified the general solution to that system of equations in a vector form, but it's still not parametric vector form. There is an additional step even still here. let's put it down, just some advice here as notes. To really get to full on parametric vector form, we must, let's put this in quotes, undo or revert or reverse the scalar multiplications and vector additions. That's a heck of a statement. Let me show you what I mean by that by looking at what we did in section 1.3. I believe it was section 1.3. Yeah, here we go. So in section 1.3, we had this right here, 6, -7, 1. That was a linear combination. But if we want to reverse all of the linear combination or all the scalar multiplications and vector additions, well, here's the first thing. This is reversing the vector addition. So now we have two vectors. This one's reversing the scalar multiplication. We want an answer that looks more like this. Everything essentially factored out, the additions undone. So going back to our 1.5, we need to undo the scalar multiplication by writing out that this is equal to x3. Multiplying a constant vector, and this is what parametric vector form is really all about. In linear algebra, we are more interested in what is this constant vector than just about anything else. The parameters, any notation we're using is not as important. What you put right in there is extremely important. We need it for null spaces, eigenvalues, and all sorts of weird stuff we're getting into. But for factoring out x3, we're leaving behind a -1, a +1, and a +1. So this is parametric vector form. Well, it's also has a parameter. The parameter is x3. And if you want to add a little bit more description, I think this is a good thing to add to your work. x3, being the parameter, is in R. So any real number, like we were mentioning earlier, same as saying x3 is free, same as saying x3 equals x3, we're just re-specifying it in our answer here. So since I have kind of notes everywhere, let me box out this. When it says get to parametric vector form, here's what you're going for. That would be the answer. Well, any questions at all, folks, on getting through those steps there? Okay, I think it's kind of a fun technique, so let's try it again. This one is kind of a warm-up problem where system wasn't too bad. There's not a lot of variables. Here's one where there is a lot of variables to account for. You have one like this in the homework where the system is kind of large and we have to navigate through it. But the work we're going to take is essentially the same kind of thing. It says describe all solutions to AX equals 0 in parametric form, where A is row equivalent to that matrix. So the author is going to do that for you as well. They have done a lot of the row operations for us. We're just going to focus on parametric vector form. So first, in order to get to this, well, notice one problem about that matrix. That's not augmented at all. That's just the original matrix A right here. So this whole thing is A without the 0 vector. That actually can cause some problems in this. It's easy when you go through this process to not have the right number of rows, like miss a particular variable, because we might have forgot that, well, there is 6 variables altogether here. This is not augmented. So for my problem, for this problem here, this would be my first step. I would take A, augment it with a 0 vector. The 0 vector came from that location up here. And really truly begin the row operations on that thing. This is a bit of copying, so sorry for the additional copying. It's going to be 1, 0, 0, 0, -2, 0, 0, 0, 3, 0, 0, 0, -6, 1, 0, 0, 5, 4, 0, 0, and 0, -6, 1, 0. Finally, here's the 0 vector. This is the actual system we're going to work on. And here's where a mistake could be made without augmenting. it's just easy to misrepresent the amount of variables you have in the system. This has x1, x2, x3, x4, x5, and x6. Kind of ridiculous, but we'll get through it. Because there's 6 variables altogether, your answer is going to be twice as tall as that one. It's going to be x1 through x6 when you get to that step right there. Also, there's going to be more free variables. So the work we do over here, we're going to be even more careful to make sure everything is arranged just right, and we can pull coefficients in a fast, predictable way. But first, it's all about the row operation, so let's look what they did for pivots on this. All set on this one, recall we need reduced row echelon form. So when we go to this pivot, we have just one little issue to take care of right here. We need to eliminate that -6 above. So we'll take 6 times this row, add it to the row above, and work from that spot. So here's the next row operation. This is a lot of copying. So I'm going to start by copying the bottom row. That's 7 zeros altogether. 1, 2, 3, 4, 5, 6, 7. It's hard to keep them in a column as you go. So penmanship starts to become a bit of a struggle on this one. It's a part of the problem, I'd say. Now, next one goes 5 zeros, a 1, and then a 0. 1, 2, 3, 4, 5, 1, and 0. I'm going to put this in here just so it looks about right. We have to copy this in, 3 zeros to start. 1, 4, -6. 0. The 0 above can't change. And -1, 2, 3 can't change. Only changes are going to be to the right or above that pivot position as well. So 1, -2, 3 goes in. Now we start our operation. Take 6 times row 2, add to row 1, and we get a 0 here. 6 by 4 is 24, plus 5 to get a 29. This will be -36 plus 0, so -36. And we're just about there, folks. We have a pivot here. Everything's all set. Here's the next pivot. 0's above and below, we're all set. And here's the next pivot. At this stage, there is a really strong shortcut that I strongly encourage you all to take. Any operation you do on this row, row number 3, will only influence this column right here and no other column. Reason for that is zeros on the left don't influence rows above or below. Nothing changes on the far right column. And so if you saw this, you are absolutely welcome to do this even on an exam setting. They're just zeros now. It's a foregone conclusion, right? So you can just scratch out your work, put 0 if you'd like. I shouldn't do that on the notes because it makes these notes unreadable. So you'll see me take this extra unfortunate step, but you are welcome to take the shortcut. So only for the sake of the notes, let's take one last row operation. All we're doing is eliminating those 2 entries right there. So a little bit more copying, we'll get through it. So 7 zeros to start. 1, 2, 3, 4, 5, 6, 7. Now that's going to be 1, 2, 3, 4, 5 zeros, a 1 and a 0. Then 3 zeros. 1, 4, -6, 0. Finally, oh, and I did make one mistake. We're eliminating that entry. We're going to take 6 times row 3, add it to row 2. So that's a 0 right there. So let me put in a 0 in this location. We're also eliminating the entry right above, that -36. Nothing to the left can change. So let me start by going 1, -2, 3, 0, 29. And take 36 times row 3, add it to row 1. You have a 0 there. But it's a foregone conclusion in this arrangement. And then another 0 here. Next thing we need are the variables. Here's x1, x2, x3, x4, x5, x6. Now the process begins. We're going to read out these equations, solve them, express the solution set in parametric vector form. Any questions at all, folks, so far? Okay, let's read out equation 1 then. It's x1 minus 2x2 plus 3x3 plus 29x5 equals 0. Let me double check that. 1, -2, 3. Okay, I think we've got that one in. For row 2, it's going to start with x4. So we'll go x4, but you know what? We don't want to write that just yet. One thing that's a little tricky of this is, well, not super tricky, but what will help us is if we always go x1, a statement about x2, a statement about x3, and then the equation for x4. We want to bring in those values because the way we arrange them absolutely matters. So let's start by saying x2 is free. Let me circle these just to show the pivot positions. I mean, that's going to help me too. So I'll write out from here, x2 is free. Then next, x3 is free. Now we have an equation we can read out for x4. It'll be x4 plus 4x5. There's a 0x6s, so all that will be set equal to 0. Next variable is x5, but that one's free. So x5 is free. Now we're doing the row for x6. And this one just looks weird. It's 1 times x6 equals 0, so x6 is equals 0. So that's what we get right here by reading out all the equations. Now we solve all of them. And notice which ones we said is free. It's x2, x3, and x5. That plays an extremely special role because your free variables right here are going to be the scalars you see in the final answer. Our parametric vector form will involve 3 different constant vectors because we got 3 free variables that will go in that location. So now we're going to solve for the basic variables, x1, x4, x6 is already solved in terms of the free variables. So here's our next line. Going down the line, we'll write out x1 equals 2x2 minus 3x3. Then it's going to be minus 29 x5. So that's how it started. When it says x2 is free, I'll just write x2 equals x2. Likewise, x3 equals, I want to put x3 way over here. What we're going to be doing is pulling coefficients, so that's a pretty effective step to take. Now for here, x4, subtract 4x5, so it's equal to negative 4 x5. If I wrote it out clear over there, finally x5 equals x5. And x6, that one's the odd one out. It's 0 no matter what you do. You have to set that to 0 to get any solution here. So here's where the free variables landed. And that means we're about ready for the solution. Now, this is the process of how we get the solution, but it's actually even faster than it looks. If you look at this boxed answer, what we do is we take the free variable, x3, put it out here, and then pull coefficients. Negative 1, 1, 1, went right in. If you copy that same technique, here's what's going to happen in our answer. We'll say x is going to be equal to, just as a reminder of what x is, you might start by saying it's x1, x2, x3, x4, x5, and x6. It's a tall vector, but it's going to be a linear combination using these things as our actual scalars or weights. So it'll be x2 goes here. Then we'll go plus, next free variable, x3. One really tall vector, then add the next free variable, x5. And whatever this results in, that's going to be our answer, the parametric vector form. Oh, I can just barely get a little more space in there. It's not too bad though. What you'll do is, if this is indicating x2, just pull all of your x2 coefficients. They're going to read out as a 2. Here will be a coefficient of 1. And then x2 never ever appears again, so just put in zeros for the rest of them. So 4 zeros altogether. 1, 2, 3, 4. So that's our first vector. Does that make sense to folks on how we're getting these values? Awesome. Then let's go now to x3. It'll be negative 3 In row 2, we don't have an x3 value, so 0. For row 3, we'll put in a 1. Then nothing else. 3 more zeros. So 0, 0, 0. 8 volunteers for the last column right here. And we'll see what the coefficients should be.
9, 0, -4, 1, 0.
There's one more 0 somewhere. It looked right, but is it at the bottom or? Oh, gotcha. Somewhere in here. Gotcha. I think that's down to, that was my penmanship. There was a 0 here and then a 0 there. So sometimes penmanship can make this a little tricky. Lined paper can help a little bit with that. So 2 zeros, then, oh, I need something other than an eraser. Then -4, then a 1 and a 0. 1, 2, 3, 4, 5, 6. Okay, we've got 6 values. That means we did it, folks. That's our parametric vector form. And we can say x2, x3, x5. These are the parameters, but we typically just say they are in R. Any particular real number you like is going to generate a solution. And here's what it looks like. It's just a linear combination of these. And you know what? If you stare at that linear combination a little bit more, there is a core definition that's related to this. Finding a parametric vector form is the same as finding a set that spans your solution space to whatever this system was originally. So let's take a look at spanning just as a pit stop right here. Spanning is, again, one of the more trickier things to get a handle on. So always deserves a little bit extra time and attention, I'd say. Where's our spanning stuff? It's got to be somewhere. There it is. Whenever we have the span of any set of vectors, we can say verbally in words, it's the set of all possible linear combinations. So that's what it would look like, all possible linear combinations. What makes it the set of all possible linear combinations as these things? They are scalars, but they're also function as parameters in that they vary. You can put in a number there, so they are parameters truly. You could have read out this whole thing for the span of a set of solutions by saying, instead of C1 through CP, it could have said X1, V1 plus X2, V2 plus XP, VP, such that X1, X2 through XP are in R. We're looking at a spanning set, essentially. Whenever we do parametric vector form, we're just happening to use X's instead of this stuff in the definition. So that means when you go back over here, this is what's expected in the answer. But when we're going further and further on in linear algebra, this is how we might sometimes format the answers. We might call this a V1. Oh, hang on, wrong V. Let me try again. We might call this one a V1. We're more interested in the constant vector than anything in a lot of problems. That constant vector and that constant vector, V1, V2, V3 are important. And now we can say the solution set to AX equals a 0 vector, same system we were looking at, is the span of V1, V2, V3, where V1 is that entire column vector right there in R6. So we'll eventually in chapters 4 and 5 use this method of parametric vector form to go back to a spanning set. And this will be an interesting object depending on what matrix and what part of the matrix we're curious about, what section we're in. But this is stuff we'll see a whole bunch in the course. Any questions at all, folks, on getting through these exciting techniques so far?
Listing the vector parameters, did we only list the free variables or?
The free variables here? Yes, it'll always be exclusively the free variables that goes in front of every one of those constant vectors. That's exactly right. Other questions so far? Okay, well, the last concepts I have on here are really just kind of quick type concept questions. We have a really powerful theorem that's going to tell us exactly and precisely when there are non-trivial solutions and when there's just the trivial solution. But other times we're interested in these kinds of matrices. We don't always consider homogeneous equations if we want to have a non-zero right-hand side. Theorem 4 is still a really important theorem. So with those both theorems in action, you'll see problems in your homework set that go about like examples 7 and 8. So looks like a good way to end class. Example 7 says, A is of size 3 by 3. There's going to be 3 pivot positions. And the moment you hear that information, if they're not even telling you what's inside A, it's not a bad idea to just write it out. I'll use just little dots to say any particular number, so long as we have a pivot in the right spot. So these are undetermined scalars going in that location. But what they told us is there's 3 pivots. So there's a pivot here, here, and here. That's just for the matrix. This one is not augmented. This is the original A of size 3 by 3. And they're asking us next, after we have a 3 by 3 matrix with 3 pivot positions, does AX equal 0 have a non-trivial solution? How do folks feel about that one? Will we have non-trivials for this one or only the trivial solution? I agree. In this case, we can read off. Well, you know what? That theorem was not the theorem I was thinking about. I was thinking about one up above here. I think I misplaced that one, but we can do this little quick fix. I was thinking of putting that theorem there. I'm not sure how I got the wrong one in. That's kind of embarrassing. Let's go back down and we'll leave that theorem alone. But we're really thinking of this one right here. Like you said, it has only the trivial solution because there is not at least one free variable. There are no free variables whatsoever. So let's go and say, does equation have a non-trivial solution? You might say, no, it only has the trivial solution. Zero as a vector with 0, 0, 0 as its entries. Since here we have to give a quick explanation, but these are pretty fast. You might just say no free variables, and that will do the job. Since there is no free variable. And we can see it in the system, even though it's not augmented. There's no way to have a free variable if you're 3 by 3 as a square matrix containing the 3 pivot positions. Well, that one's kind of fast. Does that make sense to folks on getting through that one? Awesome. So here we're looking at the homogeneous system. Here with the B, it might be homogeneous, but it's implying it could be anything now. We're wondering, is AX equal B consistent? In other words, does it have at least one solution for every possible choice of your right-hand side B? Well, this time what we can say is, note, there's a pivot in every single row of this matrix. That takes us to that statement. It's now automatically true for our particular matrix A. Then we can go back here and say, because that's true, so is this. In other words, AX equals B always has a solution. Does that make sense so far? Awesome. And how much would you want to write? You can be very terse on this. You might just say, there is a pivot in every row. This is part of an exclamation. We have to justify how we're using this theorem 4 right above. But since there's a pivot in every row, we'll say, and so AX equals B is always consistent. Recall, being consistent means you have at least one solution to your system. So we did it, folks. You could write this out different. You could say, we have a pivot in every row, so AX equals B has at least one solution. Or you could put it in your own words. It's really up to you. Any other questions or comments, folks, with that one? Okay, let's try maybe one more, and then we'll call it a night. This one's a 2 by 5 system. We're told it has 2 pivot positions and same 2 questions. This time we'll go to low. The theorems are up there, but let's see if we can do it with just from memory. First thing I would do is let's just write out a generic 2 by 5 system. So it's gonna be short. It only has 2 rows, but a little bit longer, 5 columns. 1, 2, 3, 4, 5. 2, oh, that's gonna look kind of funny. Let me try again. 1, 2, 3. I did not think this through. Let me put a little bit more space. 4, 5. Then 1, 2, 3, 4, 5. So those are the generic locations of our entries. It has 2 pivots. They can be anywhere. I usually put my first pivot there. It just seems weird not to. Then your next pivot, it could be anywhere, but I usually just go in order. They don't have to be there, but we put in 2 pivots, and this is what it would look like. Now we have to wonder, does ax equals 0 have non-trivial? I would say definitely. We have free variables, right? So we can say there is, well, we had 2 basic variables. That means 3 free variables. There is 3 free variables. And so there are non-trivial solutions. So that one's pretty fast as a concept, but again, it's using really powerful theorems to make it happen. Same question as before, does ax equal b have at least 1 solution? We'll say yes again, because now there's a pivot in every row. But if you flip this, if it was of size 5 by 2, it would be a different conclusion. You wouldn't have a pivot in every row, and you would have no free variables. So the size of these things absolutely matters. As a 2 by 5, we'll say here. Now here's one way you can answer this question. I'm trying to write these pretty short to say you don't have to be extremely verbose. You can get right down to the chase. And you can be even faster on these. It is a literal question, so you can answer it by saying yes. So now you've answered that question, and for the explain part, we just have to say, since there is a pivot in every row. I would say if you're doing an exam question, this is almost encouraged because you want to be economical with your time. You don't want to write too much that you don't necessarily have to. For your homework, writing out your full thought, that's just you studying the problem, getting all that information in your head. It's actually worthwhile writing it down. The more you can involve all of your senses in this, the more better you're going to absorb it. Well, looks like we did it, folks. That's the last question. We've only have a couple more minutes. Any last questions for our last few minutes? Okay, well, next section, it's pretty much going to look like this. Here's the preview. If ax equals 0 has only the trivial solution, then the columns of A are linearly independent. Linear dependence is, again, probably just as important as spanning. It's a little bit easier to absorb, but its importance is right up there. We'll take a look at that when we come back on Tuesday's class. Well, have a great weekend, folks. Drive safe if you're driving. And if you have any questions, I'll be happy to help out. Take care, and I'll see you all next week. You bet.